Let's look at a couple of numericals associated with the two-state Markov model, especially in this particular aspect. The most common numericals are found with respect to finding out finding out the expectation value of mu, and even constructing a 95% confidence interval associated with this transition rate or transition. So either finding out the expected value or trying to find out the confidence interval associated for the same, right? So let's try working out on that dimension. Okay, given that 20 deaths are observed, so D is 20, and the total waiting time is 780. So V, which is treated as our total waiting time, that is 780. we know that the mu follows a normal distribution with the expected value of mu and the variance of mu as the parameters. And we know that expected value of mu is nothing but d by v, as we have derived in the theoretical understanding space. So here I'll compute my d by v as 20 by 780. So the expected value of mu becomes 20 by 780, which as per our calculations comes out to 20 divided by 780, working out to around 0.025. That is the expected value of mu. Then asymptotically, right? Asymptotically, we say that any, because this mu is the maximum likelihood estimator here. Asymptotically, we see that the maximum likelihood estimators follow a normal distribution with mu and minus 1 by the second derivative. Minus 1 by the second derivative is what is the variance. So second derivative is what is the variance. So we know that the second derivative is minus d by mu square here. So we'll take it as minus 1 by 1 by d square. So minus 1 by d by mu squared. So obviously it is becoming mu squared by d. Mu comma mu squared by d are the parameters. So probably you can remember directly. So in this case, the asymptotic relationship for my maximum likelihood estimator mu is it will follow a normal distribution with the mean mu and variance mu squared by d. So now we got the mu value as this much. So probably I can say the variance can come out as mu squared. This is mu squared divided by d is 20. So this is what is coming out as the variance. So from here I can find out the standard deviation as the square root of this variance. So this works out to be something like this. So 95% confidence interval. The lower limit comes out as mean minus 1.96 times the standard deviation to mean plus 1.96 times the standard deviation. So we see that the 95% confidence interval is 0.0144 to 0.0368. So this is how I can estimate the 95% confidence interval for the transition force of transition or hazard rate. So the 95, so the mean transition rate is somewhere around 2.56%, whereas the 95% confidence interval for the same works out to 1.44% to 3.68%. Alright. So on the similar lines, let's try looking at one more numerical, a slightly a better one. A scientist identifies 1282 newborns. Okay, so we are looking at 1282 newborns and observes them during the first year of life. Wishes to calculate the constant transition intensity. So he wants to find out the mu, right? He is looking at the constant transition intensity over this period covering all types of deaths, including natural causes, right? As well as ending up as a tasty snack for the passing carnivore. If the true transition intensity is 0.18, so we want to find out we want to see it is assumed that the transition intensity is 0.18. What is the probability that the scientist observes a hazard rate in excess of 0.2? So what is the possibility that the hazard rate instead of 0.18 it is exceeding 0.2, means it is nothing but the 0.18 is the mean value. I just need to find out the 95% confidence interval, assuming that this hazard rate follows a normal distribution, and based on this trying to find out what should be the probability that this mu value crosses zero point 0.2, right? So for this I require what is D, right? So that is where we'll try to see only if this is the information that is available with me, how do I get into the calculation of D in this case? So in this case what we are seeing is we know the total lives, but we don't know what is the D, so we don't even know what is the value of the V. So the better way I look at finding out the value of V is take the integration. Okay, for the death we know what is their average life. Okay, I'll assume that between 0 to 1, right? I'm trying to find out their total life, assuming some of them have dead. We have seen that I can take between this 0 to so look at it like this. For the ones that are alive, right? What is the probability that they can be alive? E power minus mu t. So e power minus 0.8 into 1 is the probability that they are alive. So the probability that they are alive into the years. So we are observing it for a 1 year period. So their age is going to be 1, because we need to find out the expected value of the observation time. So for those things which are alive, the probability of being alive is this much, and their age if they are alive is this much. Whereas for those that they have dead, the probability that they are dead is e power minus 0.18 t into mu, right? We have seen that the probability of being dead like pqx is nothing but ppx into mu x plus t. So the same logic, e power minus 0.18 t into mu, because we are assuming that it is constant. So this is the probability of 1 that that is dead during this period, and of course for them the age is at any point they would have got dead, so we are talking about it as t. Now we are trying to integrate across all the 0 to 1, whichever is the is and mu t, so which means whichever is dead, this is going to be the equation for the same. So I would have simply written the same as integral t into e power minus 0.8 t into mu 0.18. So this I am integrating between 0 to 1. So this plus this forms my total expected value. So probably here what I can do is I can integrate these two, right? I can take 0.18 out. When I am integrating, this is of a multiplication form. So it becomes, okay, right, first I'll take e per minus 0.18 t plus integral of, I take the integration differentiation of this, which is 1. I take the integral of this, so 1 by minus 0.18. I do the integral of e power minus 0.18 t dt. Correct? Or probably let's write it slightly better. So for an alive one, we have already made it clear, e power minus 0.18 into 1. But for the dead one, we are saying e power minus 0.18 t into mu. This is the probability of being dead. Probability of being dead multiplied by the time period, age, right? This entire thing I am integrating it between 0 to 1. So probably I'll take out the constant out 0.18. Now I'll do this integration of t into e power minus 0.18 t dt. Correct? Okay, I'll take the 0.18 out. So it's in a multiplication form. So first I'll take the integration of e power minus 0.18 t between 0 to 1 minus, I take the differentiation, right? So or plus the differentiation of this, which is 1, and I take the integration of this. So the integration of this is e power minus 0.18 t dt. This is what we do, right? The first thing, we take it as the original value, e power minus 0.18 t. I do the integration plus the derivative of this, and then again the integration of the same. So this becomes 0.18 into so actually there is a small mistake here. This becomes t into e power minus 0.18 t plus integral of e power minus 0.18 t by 0.18. So this 0.18, when I am taking, this becomes, so this integral no more exists. I can directly take t into e power minus 0.18 t integrating between this. So it becomes directly e power minus 0.18 t divided by minus, so probably let me do it again, 0 to 1 t into e power minus 0.18 t into 0.18 dt. So I'll take out 0.18 and use the multiplication form of integration. So when I am using the multiplication form, I'll take the t integral 0 to 1 e power minus 0.18 t, right, minus the differentiation of t, which is 1, and again I'll do the integral of this integral, which is minus 0.18 t divided by minus 0.18. So this is what is the integration form. So obviously I'll do e power minus 0.18, and when I am substituting this t into this is directly coming out as e power minus 0.18 divided by e power minus 0.18. Then here it is coming out as, okay, I'm doing 0.18 into minus 0.18. This is going up and a plus is coming up. So integral e power minus 0.18 t by minus 0.18. This is getting integrated between 1 and 0. So this is getting here. So this is going up, minus e power minus 0.18 plus 1 by 0.18, and I am doing it as e power minus 0.18 minus e power 0, which is 1. So obviously when I am working out on this, right, so I should try to find out e power minus 0.18 minus 1. So it is this much divided by, right, this number divided by 0.18, giving me this much. So this is giving me this much minus e power minus 0.18, and obviously for the alive guys it is coming out as e power minus 0.18. So these two are going off. So obviously a minus of this, which is coming out to 9.91. So the overall expected value of V is coming out to 0.9151, right? So out of the 1282 species, the expected value is coming out to 1282 times 0.91, working out to 1173. So probably the expected value of the waiting time is 1173.24. Now I know that the mu is 0.18, right? And this is the expected value of V. So basically you can find out D also, right? D is nothing but, or probably mu is nothing but D by V. Now we know that D, now we can find out D as mu times the V. So V, we got it as 1173.24. That if I multiply with 0.18, I get my value of D. So I'll take this into 0.18, will give me the value of D. Almost 211 species must have died. And so the variance of mu, I can get it as mu squared by D. So variance of mu is coming out as mu squared 0.18 squared divided by D. This is the variance of mu. Standard deviation of mu comes out as the square root of this same, coming out to this much. So the 95, now comes the next part, the 95% confidence interval, or what is the probability that mu is greater than 0.12, right? We are interested in finding out mu is greater than 0.12, or it's as good as saying mu minus, or probably we are mu greater than 0.12 is as good as saying probability of z greater than 0.2 minus the expected value by the standard deviation of mu. So it's as good as saying probability of z greater than 0.2. So for the z we are talking about 0.2 minus 0.18 divided by the standard deviation. So what is the probability that z is greater than 1.61? So from the normal distribution tables, I should be able to get the probability of the Z greater than this 1.61 is somewhere around 1 point, z less than 1.61 is 0.94, so z greater than that is somewhere around 5.31%. So in this case the probability that the hazard rate is greater than zero point 0.2, though we have got the hazard rate as 0.18, that is the expected value of the hazard rate. I am trying to find out the probability that the hazard rate crosses zero point 0.2 by the assumption that the hazard rate follows a normal distribution with mu and mu square by d being the mean and the variances for the same. But to compute the variance and all, we had a problem because we are not able to arrive at what is the value of d in this case. So using this mechanism, we are able to calculate the value of d, which has resulted in the calculation of the hazard rate crossing a particular point in a particular value. So these are some of the quick numericals that we can observe with respect to the two-state Markov model. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.